Hi, welcome to Wix Engineering's Tech Talks show. Functional programming is often perceived as being too academic and not useful in real-world scenarios. But today I want to show you how principles from functional programming can be used to compose small, simple functions and deliver real value. My name is Amitay and I'm a software engineer at Wix. I'll just say before we begin that this is not a Scala tutorial and the video is intended for viewers who have basic understanding of the Scala programming language. So what is parsing? From Wikipedia, we see that parser is some software component that builds a data structure out of input text. For example, we can see how we can parse a string representing some data into a data object, or a string with an arithmetic expression into a tree. But also compilers, right? They take our source code as text files and need to build the abstract syntax tree. We're gonna build a simple parser for parsing JSON. I chose JSON for two main reasons. First, JSON is a very popular serialization format which we use all the time. And second, it's simple enough to understand, but because of its recursive structure, you can't parse it with tools like regular expressions, and you need something more powerful. So the first thing we're gonna need is a DSL for dealing with a JSON structure. I created a sealed trait with a generic JSON node with several implementations for null, strings, numbers, and so on. Note that the array and object node contain references to other JSON nodes. So what is a parser? Traditionally, parsing involves several steps, like tokenizing, performing lexical analysis, and building the needed data structure. But if we think about it, a parser is just a function, right? We can define our parser as a function from a string to some type A. So if we wanted to parse a number, for example, and provided the string with a sequence of characters 1 to 3, we get the number 123. But let's try to develop this idea a bit further. It would be complex to parse the entire string at once. We'd like to create simple, reusable parsers and compose them together to create more elaborate parsers. In order to do that, we'll change the return type from just the A to the tuple which contains the A and the remaining string to be parsed. This will allow us to parse the string piece by piece. So if we try to parse the number from a string 1 to 3 ABC, we'll get 123 and the remaining ABC. But as we know, parsing might fail if the provided input is invalid. In statically typed functional programming languages, we prefer capturing failures in the type system rather than throwing exceptions. So instead of just returning the tuple of AN string, we return an option of AN string. This allows us to indicate that parsing failed by returning none. We can keep going with modeling our parser by extending the input type to accept both strings and streaming data, or our output type to capture more information, like parse error description and current position in input. But we're not going to do this today, because we want to keep the examples simple. So we end up with this parser abstraction, which currently just extends a function as discussed. So let's play around with it and try to parse an integer. We'll take the prefix of the string, which consists of digits, and calling toInt on it. If no digits exist, our parser will fail and return none. And indeed it works as expected, parsing successfully a valid string and failing for invalid input. That's great. Can we use this parser to parse a number node? Unfortunately, not yet. This code won't compile because we need a parser for number node and we have a parser for int. Luckily for us, our parser is also a functor. This simply means that we can map over it like we do with lists and options and futures. So what we can do is add the map function to the trait. Map takes a function f from a to b and will transform a parser of a to a parser of b. The implementation is straightforward. We create a new function which will run our parser and delegate to the map operation of the underlying option, using f to transform the value. Having done that, we can map over our int parser and create a parser for a number node. Or we can even write it more concisely like this. So after we played with some parsers, let's think how we can parse the JSON structure. We can start by trying to parse a number node with a parser we already created. If parsing fails, we can try to parse a string node. We keep repeating this process for all node types. This is similar to the or-else combinator we have for Scala's option or try. So we extend our parser to support this combinator. Again, the implementation is trivial by delegating to the or-else method of the returned option. Now we can define the full JSON parser. Of course, this will not yet work because we only created the parser for number node. So before we continue with the other node types, we need a few utilities. Parse_char will parse successfully if the first character of the string matches the expected one. Parse_until will return everything until the first occurrence of the ending character. Next up, we will create the parser for a string node. We want to compose existing parsers we already have using for comprehension. We expect the first character to be the opening double quote. Then we take everything until the next double quote and verify that the string is ending with a closing double quote. If everything succeeded, we can yield the resulting string node. The for comprehension gives us a short-circuit mechanism, which means that if one of the operations failed, we will not continue to the next one in the chain. But in order to use for comprehensions, we need both map and flat map. We already defined map, but we still don't have flat map. As the title of the video suggests, parser is also a monad. This means we can add flat map. The implementation here might be a little more confusing than the map and OR combinators we already defined. But if you try to implement it yourself, you'd see that the types kind of fall naturally into the right place and lead you towards the correct implementation. Now the for comprehension will work as expected. As we collect more and more small, simple parsers, it becomes easier to compose other parsers. Here we see parsers for boolean and array node. We use more helper parsers here, like parse one of, which will try to parse one of the provided strings in order, and parse zero more, which takes a parser for some type A and a parser for a separator, and will return parser for a list of A. Similarly, we can create a parser for a JSON object node. We create a parser for an entry in the object, and then use it to parse the entire object using parse zero more, like we did with the JSON array. After we define the parsers for all node types, we can successfully parse JSON. You can check out the full implementation on GitHub. But I will say that you should not use this implementation in production because A, it is not complete and does not comply with the full JSON spec, and B, it is not stack safe. This is solvable by using trampolines, but out of the scope for this video. There are many JSON libraries out there. This implementation is only meant for educational purposes. So to sum up, functional programming can be used to solve real problems. We created a working JSON parser with very little code. Keep things small and simple. Every parser we wrote was about 2 to 4 lines. So even if you don't understand the exact implementation details, you can still reason about what the individual pieces are doing by the names and types. And keep things composable by using combinators. This will allow you to glue the different pieces together and gain more functionality. Thank you very much for watching. I hope you found it useful. Please join us for the next episode of Week's Tech Talks Show. If you have any questions, feel free to ask them in the comment section below. Bye bye!